He was in the tea room talking with Pandit, but I think that they should be coming soon. Okay, so let us complete the main theorem of the previous lecture. So K is an infinite field. G is a connected, smooth, algebraic group over K. And we denote by gothic G, the Lie algebra of G, and K, an algebraically closed field containing K. And for technical reason, and such that the transcendence degree of K as the transcendence degree of the prime field is larger than the reductive rank of G. So this will, okay? And oh, so this is a prime field. So, okay, so, yeah. Yeah, so well, let's keep K naught. And K naught is a prime field. Okay, so the other day we proved the following theorem that G contains a torus T such that Tk is a maximal torus of Gk. So which means that the dimension of this torus is equal to the dimension of a maximal torus of Gk. So this is precisely this reductive rank of G. Okay, so let us call this D. Okay, so we proved this. So this was proved the other time. So this was proved assuming a technical result. This was proved assuming the following theorem. Okay, let X be a regular element of G. H, the Nil space of X in G, so which is a Cartan subalgebra of G. And I put a G for Grothendieck, so it's a Grothendieck Cartan subalgebra. And then we have the following two statements. Then, firstly, if I call N the normalizer in G of H, so this is a closed, a smooth, closed subgroup of G. And its Lie algebra is equal to H itself. And so this is also the Lie algebra of H, where, oops, where I denote by H the connected component of M. Okay, so this actually was proved the other day. And let's prove the two more statements. So H is unique. Closed smooth connected subgroup with Lie algebra H. Okay, so I want to prove the uniqueness assertion here. And moreover, the normalizer in G of H is equal to N itself. And thirdly, which is the important point, if we extend the scalar to K, then HK contains maximal torus of G. Okay, so the other day we proved one, but let me recall briefly the proof because we are going to need it for the so one knows that H is unique G-Cartan subalgebra of G containing X. So this was proved earlier, and we consider the morphism that goes from J cross H to G, and we call this one phi. And so this is a map that sends some element G. So GY. So this goes to the adjoint action of G acting on Y. And so this map factors through, let's call this Q. So what we denote by G cross HN, so which is actually the quotient of G cross H by the action of N. And N acts by, so N acts on the right on a pair GY, so this is just a GN. And the adjoint action of N inverse applied to Y. And this morphism phi is equivariant for this action. So we have a phi of GY acted on by N is the same as phi of GY. Okay, because well, this is just made to work. And so since we are a field, we know that quotients exist, so we can form this thing. And so we have a map here, which we denote by psi. And The two key points is that the inverse image of X by psi is just one point. It's the image by the quotient map of the unit element and X itself. So this is a single point. And so we get that psi is generically finite. So this is one assertion. And a second assertion that we saw the other day is that the differential of phi at the point Ex is surjective. And phi is generically smooth. And its image contains an open subset of G. And so we obtain that the factorial map phi is dominant. And if we combine these two assertions, that phi is dominant and generically finite, so this gives that the two of this are the same dimension. So the dimension of G is equal to the dimension of this quotient. And this is the dimension of G minus, well, plus the dimension of H. And so this is the dimension of this scheme, and N is acting freely. So when we make the quotient, the dimension decreases this by this amount. And since G is smooth, the dimension of G is the same as the dimension of its Lie algebra. And so we get this equality. And since by definition, N is defined as the normalizer of H, so it is the set of those elements G whose adjunction stabilize G. We also have that the Lie algebra of N clearly is contained in the Lie algebra, which is a normalizer in G of H. But this is H itself, because H is a Cartan, because H is a G-Cartan subalgebra. And so this implies that it is equal to its own normalizer. And hence we have the hence. So this equality gives that the dimension of H is equal to the dimension of N, which is smaller than the dimension of the Lie algebra of N. And this is smaller than the dimension of H because of this containment. And so this implies that the dimension of N is equal to the dimension of its Lie algebra. And hence N is smooth. Well, at the origin, and smooth everywhere. We are over a field, and one knows that over a field, smoothness at the origin implies smoothness everywhere by translation. And further, this equality of dimension gives Lie of H is n. So, okay, so we have, of course, this is the Lie algebra depends only on the connected component. So if we define H to be the connected component, H is smooth, H is smooth. So we define H to be the connected component of N. So it is smooth and connected. And its Lie algebra is H. And it is a unique one, because if H prime is smooth, connected with Lie algebra H, but then, of course, H prime acts on H by its adjoint action. So H is contained in the normalizer in G of H, which is N. And since it is assumed to be connected, it has to be contained in the connected component, which is H. And now, since H is smooth connected, and this one has the same dimension, so H prime is equal to H. So so H is unique, and what can we say about the normalizer? If we look at the normalizer of G in H, so this group stabilizes certainly the Lie algebra of H. And so this is the normalizer of H, and so this is N. And so the normalizer of H is contained in N, and also N normalizes its connected component, which is H. Hence, we have equality. And the normalizer in G of H is N. Okay, so we have proved this. And now we want to prove that this statement. Okay, so now we extend scalars from the given ground field to this large algebraic closed field. And for brevity, I denote GK simply by G. So we will omit the subscript GK. So now our base field is the algebraically closed field capital K. Okay, so we saw for our regular element X that the adjoint action of X acting on the quotient G over H is injective. Okay. And I claim, or rather Grothendieck claims, that there exists at least one point H1 in H of K such that the adjoint action of this element H1 has no non-zero fixed point on the quotient G over H. So that is that, which means that the determinant of the identity of G over H minus the adjoint action of H is non-zero. Well, so let's prove this claim. So assume that the map from H, assume that the map from HK to well to the well to K, which sends an element H to this determinant. Assume this is identically zero. Well, hence, and so note that so this map, so this map corresponds to homomorphism of K algebras from the coordinate ring of GA, so that is from K of X to the coordinate ring of our group H, and so it sends H to some polynomial P. And so this says that then P is is zero. So it's is a zero polynomial. Okay, because so this is a K algebra of a finite type. And so this is a polynomial that vanishes on all rational points. So it is a zero polynomial. And P is also zero on infinitesimal on points in the Lie algebra of H. So these are the point of the form 1 plus epsilon x. No, I'm not going to call this H with H in well. What I mean here is that I consider the kernel of the natural map from the points with value in the dual numbers over K, and so okay. So since P is identically zero, it is also zero on any points over this ring. And in particular in those points which are in the kernel of this restriction map. And so those points can be written as identity plus epsilon for something in the Lie algebra. And so this gives, and so this gives that the determinant of so if I apply this to such a point, what does this give? Well, yeah, yeah. Yeah, yeah. So yeah, so what I want to say is that if yeah, so and then if we add to such a point, so what we obtain is the adjoint action of such an infinitesimal point is something like epsilon times the adjoint action of H. And I'm confused because of the epsilon now, but yeah, yeah, yeah. Oh, yeah, okay, yeah. Yeah. So what I want to say is that if we differentiate this, we obtain the statement that the determinant of the adjoint action of H is 0. And so the adjoint action of, okay, so this is the adjoint action. So if we differentiate, we obtain that this is identically 0 for any H in H. Okay, so I'm sorry, I was a bit sloppy here, but so the idea is that if one differentiate this, maybe so. So here H is a point in the group, and here Y is an element in the Lie algebra. And what I was trying to explain is that this follows from that, and my explanation is not clear, but this is what you obtain if you write properly what the Lie algebra is. But so this is not true because we know that there exists at least one point where this map is injective, and so this is a contradiction. And so this proves the existence of an element H1 like that. Hence, there exists a point H1 as in the claim. Oh yeah, I now remember. So if we do this, we obtain something like epsilon at H, but it is acting, formally it is acting on something like epsilon H. And so actually we can simplify by this epsilon, and after, when all natural identifications are made, we do obtain the adjoint action of the adjoint action. Okay, so maybe this one I should call it Y, because this is a Lie algebra element. Okay. And so by differentiation, we do obtain this. And so we obtain that for a generic point of h of k acts like this. And now we can conclude the proof. Mm. And now we consider a similar diagram. Consider now so the map from G cross H to G, and let me call it again phi, even if it's not the same one. So it is a map that sent GH to GH G inverse, and again we make n acts on the right on G cross H by so GH acted on by N is GN N inverse H. So is that the correct action? So if I do this, no, yeah, I think it is, yeah, it is probably something like this, because if we, yeah, yeah. Well, so we want this map to be invariant. So this has to be this, okay? And so this so this factors through the quotient, and we have here a map psi. And we and so the differential of phi at the point, the identity element and CH1 coming from the previous claim is a map going from G to H to G, which send an element y t to t plus the identity minus the adjoint action of H1 on Y. And okay. And okay, and so by what was said above, so this map restricted to the quotient. So on the quotient G over H, this is injective by our choice of H1, and it is bijective. And therefore, we obtain as before that phi is smooth. At this point. And so we obtain that psi is dominant. Okay, so this gives but also the dimension of this. So this is the dimension of G plus the dimension of H minus the dimension of N. And so this is 0 because we saw that H actually, well, H is the identity component of N, so they have the same dimension. So this is the dimension of G, which is the dimension of G. And we obtained that psi is generically finite. Okay. And well, actually, I didn't really need the second part. Well, dominance is enough. Well, so the fact that psi is dominant. So this implies that G contains a dense open subset U such that every rational point in U is contained in a conjugate of H. Well, yes, because so this map contains the image of phi contains an open set U, and for U in the image, any element in the image is contained in some conjugate of H. So we have this this property, and now let T be a maximal torus of G. And so I recall that now we are over an algebraically closed field, so there are maximal torus. And by a theorem of Borel, the union conjugates G minus 1 for G rational point contains also a dense open subset. And actually, the proof is the same. The proof is the same. One considers a map G cross T on G, and so well, for a maximal torus, we know it has finite. A maximal torus is a connected component of its normalizer, and everything we did applies here. Okay, so the conjugate of of T, so they are dense, and so um, um, and and so the union of this conjugate meets the open subset U, and uh, and so uh, replacing T by a conjugate, we can assume that T intersected with U is not empty. And then if we call V this intersection, so this is a dense open subset of T. Okay, and okay, and now the trick used by Grothendieck, well, one could do without that trick, but the trick makes our life easy. And so since the transcendence degree of K over K0 is bigger than and since K is algebraically closed, our torus is necessarily split. So it is a product of it's a GM to the D. V contains an element of T of K, so which is K star to the D. So it is some element T1 TD, which does not belong to any proper closed subgroup of T. Because for this, it suffices that T1 to the N1 times TD to the ND is different from 1 whenever for any integers N1 up to ND, not all 0. Okay, because any subgroup of T is defined by the vanishing of some character. And so if we take the TIs algebraically independent, we are sure that such an element is not contained in a closed proper subgroup. There has to be element like this in this open dense subset. Okay, so let's call T this element, and T is in V, and by the definition of V, it is contained in a conjugate. So there exists some G in T of K, such that T belongs to the conjugate JH GH minus 1. But so this is a closed subgroup of G. And so since T, by this property of T, so we obtain that the maximal torus T itself is contained in GH, G inverse. And so we obtain that G inverse T, G is contained in H. Okay, so this proves this result. So that, well, so we have this H, which we can call a Cartan subgroup. And it has to contain a maximal torus. And so the argument is that so both these so now if T is a maximal torus, both these maps are dominant, and so this means that some element of T is well, a generic element of T, that is T contains an open subset of elements which are contained in a conjugate of H. And by picking a T, an element general enough, we manage to have T itself entirely contained in a conjugate of H. Okay, and so we obtain that a Cartan subgroup. Mm-hmm. No. Yeah. For any element in V, there exists a G. Yes. Yes, absolutely. Yeah. So V is a set of element G1 in G, such that there exists a G such that G1 belongs to GH inverse. Okay, so yeah, so G depends on T, but since T is a generic element, that is well, one could say that it topologically generates T. Yeah. Okay, so this works like this. Okay. But in fact, this argument of topological generation is already used by Grothendieck in 1858 in his exposé in the Chevalet seminar to prove the Borel theorem. So Grothendieck, it seems, never forgets anything, because he used this argument already in 58. And when he needed it later, okay. Yeah, well, actually, this argument is used by Borel. So yeah, so the argument that, so the proof of the theorem of Borel, so Borel's proof uses the fact that a maximal torus is its own centralizer. And in fact, there exist generic elements in T. So you can find a single element whose centralizer is the torus itself. And so Borel's proof, you just take a faithful representation on some vector space of V. So the torus acts by a finite number of characters, and you take any element. So the kernels of the characters are hypersurfaces in, well, codimension one subtoroid in T, and you take an element which is not in the union, and it's a generic element. And so when he wrote his proof of Borel's theorem in 58 already, so Grothendieck didn't use this argument with a faithful representation. He already used this argument. And so the idea is not coming out of nowhere. So it's part of the classical theory that, torus of an algebraically closed field, well, it's almost generated by a generic element. And so Grothendieck so he used it in a very clever way here. Okay, so this completes the proof. As I said, so this technical result completes the proof of the existence of a maximal torus in any smooth affine group of an infinite field. And in the remaining 20 minutes, I will start explaining things about the representability of normalizers and centralizers. Okay. So this completes lecture 12. And let me go back to what is called lecture 11 in the notes. And lecture 11 is representability. Representability of normalizers and centralizers. Yep. Yep. Yeah. Oh, because T is in T, so it's in the, so this is a closed subgroup. So this is uh, uh, so the claim is that there is such an element inside the open subset V. And V is precisely the set of elements in G which are contained in some conjugate of H. And so no, I didn't prove it. It's well, it's left to the reader. Yeah, I couldn't find a neat proof, but so the idea is that if all elements like that were contained in the complement of V, which is closed, so if we take elements which are algebraically independent, the powers are also algebraically independent. So actually the subgroup that generated is contained in V. And so since we have a field, this means that the closure of the subgroup is contained in the complement, in the closed complement of V. And so we obtain a closed subgroup which is contained in the complement of V, and then T itself is contained in the complement of V, which is not possible. But you're right. I skipped this argument because I found it was not nice to write the details, but the details are not written. Grothendieck didn't. He just say, well, it's clear that V contains, and so I think the argument is just what I said. All those generic elements cannot be in the complement of V. And once you have one element like that in V, then we are done. So, okay, so we want to prove a very useful result about representability of normalizers and centralizers. And the beginning is very abstract. So please be patient, because when I first read the argument, well, I didn't understand what Grothendieck was doing, but once you understand it, it's a very nice argument. And so let S be our base scheme and fix some scheme. And we define the Weyl restriction of scalar. So the Weyl restriction, which we let us denote it by, so this is a calligraphic R, so the restriction of scalar. No, yeah. So for any Z scheme Y, define the functor, which we denote by restriction of scalar from Z to S of Y, or it is also sometimes denoted by pi Z over S of Y by, so for any scheme T over S, the T points of this restriction of scalars. So these are so this is okay, so this is yeah, so this is the white points of this. Okay, so it's usual, for instance, to consider this restriction of scalar functor in the case, for example, of a field extension. So if you have an algebraic variety over C, you can regard it as a variety over the real field, and then it has twice the dimension. And so this is a remark. So the usual case is that if S is affine and spectrum of A, and Z is a spectrum of B with B a finite A algebra, well, locally free over A, say of rank D. Then it is easy to see that if you restrict, say, the affine space over S, sorry. So this is the affine space over S of dimension n times D. Okay, so this is an easy generalization from the case if you take a variety over the complex number and regard it as a variety over the reals. But we are going to do something completely different and consider, and so here this is the Y, which is, well, rather big over Z, so it is a affine space. But we want to consider a rather unusual case. Consider now consider case where Y is a closed subscheme of Z. Okay, so what do we get? And that is we consider, so that is we have a closed immersion of Y into Z. So this is a closed immersion. And for any D over S, so I claim that, so if we look at this restriction of scalars, that Y over Z, no. What is this restriction of scalar? So there are two cases. So this is the set with one element if the inclusion is an isomorphism. So this is the map obtained by base change, and it is the empty set otherwise. And so why is that? Proof. So by definition of the restriction of scalar, so this is Z of ZT into Y. And so this is also the same thing as of a ZT of ZT to YT. And so this is a set of maps. This is a set of morphism F of ZT to YT. Yes. Thank you. Yep. And here also I miss the T. So we have this functor, and we take at its value on T. So this is this. And so these are the morphism of ZT schemes. And here we have, of course, the identity map. And so this is our closed immersion obtained by base change. And we want this, so these are, those F such that we have this commutative diagram. Okay, so these are those F here. And the condition is that this composition is the identity morphism of this. And since this one is a closed immersion, so this implies that if such an F exists, so this closed immersion has to be an isomorphism, and F has to be the inverse. Okay, so F exists if and only if tau T is an isomorphism. And then F is the reciprocal isomorphism. Okay, so instead of writing point, so there is a single element which is the inverse of this closed immersion if it is an isomorphism and it is the empty set otherwise. And so so let's try to so here we have our base S, and over, well, so this is the way I picture this. So over each fiber, we have a big scheme, which is ZS, and we have a maybe smaller scheme, that scheme which is YS, and so so this strange functor is representable if and only if so if this restriction of scalar is representable, it is represented by the closed the unique, well, the closed subscheme of S over which the inclusion Y of Z is an isomorphism. Okay, so this is called the scheme of coincidence. In the book by Bosch, Lütke, Baumherk, Reynaud, this is called, I think, the scheme of coincidence. Okay, so we have these two schemes. So Y contained in Z over S, and we consider this restriction of scalar. And if it is representable, then it is representable by the largest closed subscheme of S over which Y and Z agree. Because it's, well, because we see that we have a morphism from T into this functor, if and only if the pullback of Y and Z to T agree. And well, you see it is well, either the empty set of one point, and so well, so this functor is how does one say unramified over S. So well, so it has to be, if it is representable, it is represented by a closed subscheme. And we are going to prove that it is the case under some hypothesis. And let me just take the hypothesis. So since time is running short, I will write a provisional definition. So definition provisional. So I will give the true definition next time. We say that Z is essentially free over S if locally the ring of a function is a free module over O of S. Okay, so the precise meaning of locally is written in the notes. So this means when it's local on S, so you can cover S by open affine subsets. And so the inverse image, you can also, it is covered by often affine such as the ring SS. And the theorem that we will see next time, theorem. If Z is essentially 3 over S, and we have a closed immersion like that, as we said before, closed immersion, then the value restriction of Y is a closed subscheme of S. Okay. So we will prove this on Thursday. And the trick is that we are going to apply this to the case where S is our group scheme G of another base S prime, say. And then the value restriction will precisely be a centralizer or a normalizer of a subgroup. So it's surprising that this very general result about the value restriction of a closed subscheme, it covers all possible cases of normalizers and centralizers of subgroups and also fixed points and everything. Okay, so this is the goal for the next lecture. Okay, thank you.